Hi, class. So the screen that you're seeing is actually from lesson 4.1. If you didn't get to it or didn't look at the next lesson notes of the activity, do not worry at all. Okay, so the only purpose of that was to discover what the derivative of a sine function or a cosine function is. So I'm going to just quickly show you. So right now you got a sine function here, as you can see with the blue graph. And your derivative function, as I've shown you in the past with decimals, is going to appear in black. So as I drag this file forward, so what it's plotting is the slopes of the tangents. So the slope of the tangent when the angle value is 0 is at a maximum because it's at the point of inflection. Remember, we talked about that sort of thing. And then the tangent slopes are decreasing. And as we just sweep through the rest of this, the graph that is created here, as you can see, mirrors exactly a cosine graph. Oops. Okay, so you get exactly a cosine graph there. So the derivative of sine x is cos x. And if we change the function to cos x, we can do a similar little exploration here. So again, as we get to the peak here, so the slope of the tangent is 0, so we're crossing through there. Now the graph here isn't quite that familiar, but as the tangent moves along, so again, these red dots are plotting the slopes of the tangent at each point. So it may not look too familiar, but blue is cosine, the black is negative sine, so a sine function that has been reflected in the x-axis. All right, so that's all 4.1 was all about. It's just to do a little discovery. So like I said, if you got through it, great. If you didn't, no big deal. I'm going to just quickly go through in a moment the 4.2 lesson, just relatively quickly. Nothing too extravagant though. Okay, so hopefully this isn't too challenging for you. So there's your 4.2 with a quick little review that the derivative of sine x is cos x, and the derivative of cos x is sine x, or sorry, negative sine x. All right, so just to get through some examples here. Now, the reason why you might see some brackets in here, so I'm using a previous file to help me out get through this video and just give you some extra little tips here. So much like any other functions you've dealt with, coefficients can be treated separately. So you have to worry about us differentiating the function that you're given with respect to the variable that you see. So in part A, you have the derivative of this function would be focusing on the derivative of sine x, and the derivative of sine x is cos x multiplied by 2. So there's your answer. And in part B here, again, focusing on cos x, derivative of cos x is negative sine x multiplied by negative 6. And that's what you get there. And then again, moving right along, you've got two different functions to worry about. So you have cos x and sine x here and here. Right? So the derivative of cos x is negative sine x. So this would give you negative 3 times negative sine x. And then the remaining part, negative 5 times derivative of sine x. Derivative of sine x is cos x. So you keep the minus 5, and then you get the derivative of sine x, which is cos x. Now, simplifying obviously is easy. This is just the coefficient multiplied by a negative, 2 negatives here, and nothing really to worry about there. So those are the simplified results for B and C. So the basic premise for taking derivatives of trig functions is pretty straightforward. The only thing that you might get a little tripped up on is when constants become symbols like pi, because that's just a constant. Don't be afraid of that. And instead of using the letter x, you can have theta, but you can take derivatives with respect to any independent variable, so don't get intimidated by that at all. So let's run through the next one here. So here you're treating pi as a constant, so that's negative pi, so you want the derivative of sine x, all right? So that's where you have to be very aware that you're just taking the derivative of the sine x. This is a constant. 5 pi, 5 times 3.14, that's just a number. And the derivative of a number is That pause was dramatic effect if you weren't sure. Derivative of a constant is 0. So your derivative function is negative pi. Keep that coefficient the same because that has nothing to do with the variable. Derivative of sine x is cos x, as you can see there. And then plus 0 because the derivative of 5 pi is 0. And then quickly simplify that. And then similarly here, now notice the notation changes slightly. So you got h prime at theta. Keep the coefficient of a quarter. Derivative of sine theta. Just because the variable changes, don't worry about it. So the derivative of sine variable equals cos variable. Okay. So there you go, or cos angle, whichever you want to refer to it as. And then similarly, you got negative 3 pi. Again, pi is a constant. Don't get intimidated by that. It's not a product rule in any way. So you're just looking at focusing on the derivative of cos theta. Derivative of cos theta, there's your variable theta. So your derivative of cos angle is negative sine angle. Derivative of cos is negative sine. Now, if you're wondering what happened to the negative sign, well, this was a negative. Derivative of cos produces a negative, so two negatives produce a positive. So just jumped a little bit ahead. Okay, so hopefully that doesn't bother you too much. All right, typical question that you've seen before. Find the equation of a tangent line. All right, 2y equals negative 2 cos x at the point da, 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 da. Now, if you're looking for a visual on this, just to quickly go to Desmos, again, if I can get that file up really quick. So the file is negative 2 cos x. So negative 2 cos x. So there's negative 2 cos x. So what we're really looking for, just to go back again to the question we're dealing with here, at the point where theta is pi by, or sorry, x is pi by 3, and the y value is negative 1. All right. So getting back to that Desmos file. So we're looking at pi by 3. Now you notice the rating values aren't listed here, but you want the y value to be negative 1. So we're like, where's that y value equal to negative 1? Well, you can locate that roughly about here-ish. Sorry, having a little mouse issues. Okay, so that would be roughly pi by 3. So your y value is about negative 1 right about there. Okay, and pi by 3 is 1/3 of pi, so you know you should be in this part of the graph anyways. So we're trying to find the equation of that dotted line. So that gives you a little visual as to what you're trying to do. For the math portion of it, it's nothing different. We still need the slope of the tangent, which is your m. And then from there, we can use a point on the graph to find that equation of the tangent. So if we take a look at the process here, so m is the slope of the tangent. That's what I'm indicating as far as the lesson handout is concerned. Whoops, sorry. We'll go down this way. So laugh out loud, just trying to do a little comic relief. That means find the derivative. So we need the slope of the tangent. So we have to find the derivative at x equals pi by 3. So because your derivative is going to help us get the slope of the tangent. So the tangent slope is determined by finding that derivative when x is equal to pi by 3. So here we have the derivative function, derivative of negative 2 cos x. So again, if you're wondering where the negative went, derivative of cos x is negative sine x. And the two negatives then will produce a positive for the 2. X value is pi by 3. Gotta know your ratios. Remember you did your ratios way back in previous courses. So I got a little reminder triangle there to help you out, or if you want to use any other technique that we've talked about. So the slope of the tangent at that point is √3. Once you've got that sorted out, then to find the b value for the y equals mx plus b format, easy peasy. So again, you take the point that you're given, That's your x and your y. You have your slope of the tangent as √3. And now you cannot use decimals, so this is where it's going to be a little tricky. And sometimes your answers at the back of the book may not match perfectly, but your simplification process really depends on your algebraic skills. Okay, so again, here I'm just subtracting on both sides to isolate b. This is a common denominator between these two steps here. And then write the equation. It does look very strange, and the back of the book may have even stranger looking things when you're checking your answers, but something I'll have to deal with in terms of dealing with solutions, as you always have with this textbook. And that's essentially it in terms of dealing with the concept here. So this is 4.2. Hey, please take these practice questions with a grain of salt. Don't expect that you need to get them all done. Do whatever you can. Make sure you read through the examples in the textbook as well. They will be helpful. I did put some extra questions in the past, so just to highlight some of the challenges you're going to be dealing with in terms of later on with derivatives. So this extra question involves using the product rule. All right, so this is the example function, and I've got it set up a little bit like what we did in class prior to our extended break, unfortunately. So you'll notice that I've identified the two different functions that you're given. This one has an x variable. This one also has an x variable, but all of this in between here, that's part of your angle. So this is like saying cos theta, big angle. It's very ugly algebraically looking, but just treat it like an angle. So here's your first function, f, and then your g function, all right? So what I'm trying to demonstrate here, which we'll talk more about, but just to give you a little insight. So the derivative of that smaller function, f, pretty easy, derivative of -3x. The way you should think of taking the derivative of the other function is a little bit more complex. That's what I've got written down here. So it's a little bit different in terms of how to deal with it. So the derivative, now I probably shouldn't have put the, well, I've got it in here, but anyway, we'll deal with this. Maybe I might have to correct that. So this is your product rule. So if you look at the pattern, so we have f prime g. There's f prime. Here's g. So the tricky part comes from the portion of the product rule where it's plus f g prime. So plus f, now remember f is the 3x. And g prime, now here's where things get to be a little bit sneaky. The function you have is a cosine with an ugly angle. Your derivative of cosine is negative sine of whatever angle you have. So it doesn't matter if it's x, doesn't matter if it's theta, doesn't matter if it's 10w, it doesn't matter if it's this big ugly power. That's your angle. So you keep that the same. As you know though, with chain rule, much like we did with polynomials, you need to take any derivative of basis. Now here what we're doing is we're taking the derivative of the angle. So the chain rule requires us to take the derivative of this entire angle here. So everything after the sin is considered part of the angle, including that exponent of 3. So if you just focus on that portion alone, then you'll see that it's the power. And to use the power law to take the derivative of this, well, as we've done before, 3 becomes a coefficient. Keep the base the same. Decrease the exponent by 1. And again, another chain aspect here. So a chain aspect of taking the derivative of the base here. Derivative of x squared plus 5x gives us another multiplication of 2x plus 5. So everything inside this blue set of brackets that you see here, from here to here, is just the derivative of g. Very ugly and very messy, but just wanted to forewarn you for some of the things that are up and coming in this wonderful unit. All right, there's another example for you to kind of take a look at. This is very different simply because the way it's set up. So you notice the exponent belongs to the cosine. How do you know the exponent belongs to the cosine and not to the angle? Well, just like you write powers, exponents are always up and to the right of what you're referring to. So this 2 belongs to the cosine, which means another way of writing this is that. So when you're taking the derivative, what you have to keep in mind here is that the function that you're given is actually a power. So you have a power here. And this is the base on the inside. All right. And this is your power. So you treat this as a base. There's your exponent. So the power law says take the exponent, use it as a coefficient, keep the base the same, decrease that exponent by 1. Chain rule tells us don't forget to take the derivative of the base. Derivative of the base, well, we have a cosine function. So the derivative of cosine is negative sine, must maintain the same angle. Chain rule also warns us that we must take the derivative of the angle. So derivative of 3x gives us 3. So the final simplified derivative is negative 6 cos 3x sine 3x. Okay, so hopefully this little video will help you get through a few things. And lastly, don't forget your special triangles. Right, so you'll probably need them to get through a few things. There's 1 or 2 questions in the book you might want to review that also have a double angle formula or compound angle formulas that you may need, but I'll leave that up to you to decide whether you're going to work with it or not. All right, hope you enjoyed the lesson and please stay safe.